Hey everyone, special Cal 2 lesson for you today. We've talked about how to find the area under a curve, the slope of a curve, volumes generated by regions defined by curves. But now how about the length of a curve itself? Let's say I got some smooth, the differentiable function f, and I want to find the length there in blue of f on a to b, from a to b, where a and b are x values. I'm going to denote the length with the lowercase s is often called the arc length of the curve, or it's just loosely speaking the length of the curve from a certain point to a certain point. Now, provided that that function again is smooth, how can I find the exact length of that curve? Well, we're going to start in familiar territory, partition our interval AB. In this case, I'm going to make 6 subintervals, x sub naught to x sub 6. But I'm not going to draw rectangles, I'm going to draw points. And from those points, I'm going to connect the dots with red line segments to form a segmental path. And you can see here that red segmental path will be a decent approximation of the length of the curve in blue. I've also labeled a few points: x, f of x sub naught, f of x naught, x sub 1, f of x sub 1, x sub 2, f of x sub 2, and so on and so forth, all the way up to x sub 6. And of course, the way I can find the length of all of those segments is to construct a right triangle from all of those segments. That's certainly one way to do it. So that first length there is going to be x1 minus x naught. That's the leg of that first triangle. The other leg of that triangle is f of x sub 1 minus f of x sub naught. And from there, of course, ladies and gents, we Pythagorate those triangles. First one, x1 minus x naught squared plus the y coordinates differenced squared, square rooted. That's the length of that first red line segment. And I can notate this more crisply by knowing that x1 minus x sub naught is delta x1, the first delta x. That's what that means, the first delta x. Of course, I can continue like this for the remaining 5 line segments. Dot, 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 all the way up to delta x sub 6, the whole thing squared, plus f of x sub 1 minus f of x, or f sub 6 minus f of x sub 5. Notice here, delta x sub I, the ith subinterval, the ith delta x, is always going to be xi minus xi minus 1. Knowing this allows me to crisply compress this info into a summation. Delta x sub I, the whole thing squared, plus f of x sub I minus f of x of I sub 1 squared, square rooted from 1 to 6. Now I'm going to do a little bit of fancy algebraic jujitsu here. I'm going to pull out a delta x sub I squared from that second term in the radical, leaving me with this. So those white delta x sub I squareds cancel. We'll generate the original, but the whole point of doing this was to factor out a delta x sub I squared from inside the radical. So inside the radical, first of all, I can rewrite like so. Bracket, bracket, big root, big roof. And now I'm just going to apply familiar exponential slash root properties. And here we are. I'm going to apply that down here. And that allows me to yank out the delta x sub I squared from the radical as just a plain old delta x sub I that you see hanging out on the right. Now, I'm going to copy the same thing here. I to 1 equals 1 to 6. Of that same thing, there we go. And notice here I've rewritten delta x sub I as xi minus 1. Subscripts, of course. Now visually, look, I'm going to construct a better approximation. Instead of going from 1 to 6, what if I go from 1 to 12? What if I construct 12 segments to form a more detailed segmental path? So same deal, but from 1 to 12. What does this look like on the picture? Well, I'm going to draw 6 yellow dots in between the 6 red dots. I'm going to connect all 12 dots with line segments to form a much better approximation, a much better segmental path. So let's first I'm going to get my x coordinates on the table, so you see me changing all of the x's to x sub 0 all the way to x sub 12 there on the x-axis. And now I'm going to very meticulously put together a segmental path. And look at this, it is such a better approximation than the red segmental path. So this yellow segmental path is really getting close. Really getting close to the actual length of the function on the interval AB. And now, you may have seen this coming, but we employ the calculus, a classic move from calculus, which is to, once we get a decent approximation expression, to just, hey, get the exact thing by limiting as n goes to infinity. Here we are. Whatever that is, that weird expression is, that is the actual length of the graph in blue. But notice, I can notice something special. The inside of that bracketed term is the slope of the secant line. So we're bringing some Cal 1 knowledge here. That is the slope of the secant line, connecting x sub I minus 1, f of x sub I minus 1 to x sub I, comma, f of x sub I. Let's put a picture of that. So the slope of that white line segment is going to be the inside of that bracketed term. But notice, again, this is why f of x being differentiable and smooth is important, because now I can employ something very useful. I know that the slope somewhere on the curve itself has to equal the slope of that secant line. That's essentially the mean value theorem for derivatives, is what I'm stating here. We know that there's some x coordinate, x sub I star, in between x sub I minus 1 and x sub I, for which f prime of x sub I star will equal that bracketed term, the slope of the secant line. And that's all I'm saying down here. So again, that x sub I star just means x sub I star is strictly in between x sub I minus 1 and x sub I, not including the endpoints. We can say that because it's a differentiable smooth function. There are no sharp points in the middle. In other words, I can replace that entire bracketed term with a derivative term, x of x sub I, f prime of x sub I star. And there we go. Looks much nicer, still a bit weird, but now, this guy that I've underlined in blue, he fits the form of, you guessed it, a definite integral. So just as a reminder, the definition of a definite integral, not the FTC, fundamental theory of calculus, the shortcut to calculating a definite integral, but the definition of a definite integral is that limit as n goes to infinity of the rectangular areas. So that's what I'm doing here, more abstractly, of course. Again, this is the definition of a definite integral. So how about we just let g of x sub I star equal the square root of 1 plus f prime of x sub I star squared? And apply the definition. We'll apply it very well to this expression. So, arc length is the integral from a to b of g. Now we sub back in for g. Square root of 1 plus the derivatives squared. Integrated from a to b. That weird thing, unexpectedly, this suave formula is the formula for the length of the graph from a to b, provided the graph is smooth, provided its derivative exists everywhere in AB. That suave formula gives us the actual length of the graph. That's really crazy. So this is another infinite geometric expansion to our geometry repertoire. Very cool stuff, very cool stuff. So our Cal 2 knowledge has been applied for a fourth, fifth time to give us some infinite expansion to our geometric abilities. Let's apply this to a concrete example now. Suppose I have this function here, and I want to find the actual length of that function, the actual length of the graph of it, from x equals 1/2 to x equals 2. I'll put a visual up in a second, but for now let's just run the computation. First I need the derivative. I simplify it a bit to get that, and now I want to square it, add 1 to it, square root it, and that's the thing I want to integrate from a to b. Hopefully it turns out to be a nice expression that's easily integrable. So let's see, I'm going to square the derivative, so same thing as squaring the 1/2 and multiplying by the square of x squared minus x to the negative 1/2. So there we go. I can pull out a 1/4. It is 1/4. No, that middle term, 2x to the 0, is just 2. And so I can rewrite that entire expression on the inside of the radical without any square roots, without any parentheses, I mean. Like so. And that entire thing inside the square root is something that's actually factorable. Because that 1/2, I can rewrite that as x to the second times x to the negative second. And now it's a straight application of FOIL. In reverse, factor. So there we go. Inside is that guy squared. Square root of that guy squared is him. And he is easily integrable. He is a nice, not quite polynomial, but still very nicely integrable. And here we are. Throw in a 1/2, throw in a 2, take the difference, and we're going to come out to get, and you can verify this for yourself, 33/16. That's the actual length of the graph from x equals 1/2 to x equals 2. So roughly this graph is a parabolish thing, a little tilted, but it's a curvy thing, pointing up, and the actual length there in blue from 1/2 to 2 is 33/16. So appreciate what you're able to do now. You couldn't do this stuff before this video, but now you can. You can find the perimeters of, or lengths of infinitely many weird shapes. Now let's confirm, using this formula, that the circumference of a circle is 2 pi r. Again, this is not really a proof, because the most common definition of pi is the ratio of the circumference to the diameter. And if that's the definition of pi, then of course the circumference is going to be 2 pi r. But let's just confirm that this equation is in keeping with what we already know. So I'm going to take the derivative of that semicircle, apply a bit of chain rules. Can't forget the chain rule. Got to remember all your Cal 1 rules for this lesson, and these batch of problems that go with them. So I square the derivative, going to add 1 to the square of the derivative. I'm going to write a simplified expression for 1 to the square of the derivative before I plug it in inside the root. That 1 I can change to r squared minus x squared over r squared minus x squared. Adding that to x squared over r squared minus x squared gives me r squared over r squared minus x squared. Stick that in right under the root. I can break that one root up into 2 roots. The top root of r squared is an r. I can pull that out. I get a dx over the square root of r squared minus x squared. That looks very familiar. That looks like an inverse trig boy of some sort. Inverse sine, if my memory tells me reliably. I'm going to factor on r squared from the bottom. Now I can yank out the r from the bottom, right outside. And x squared over r squared, I can rewrite that as x over r. The whole thing squared. It is high time to u sub and get some inverse sine action going on. U is x over r, du is 1 over r dx. Gotta multiply by 1 over r, but means I gotta multiply by an r. I don't pull that regular r to the front because I don't need it in my substitution. So I have r squared over r out front, which is just r. That's what you see up there in red. All times the integral, definite integral of du over the square root of 1 minus u squared. Now it's definite integral, I gotta accurately convert my x values to u values. Negative r, when I stick him in that blue expression, gives me a u value of -1, and positive r, when I stick him in the blue expression, gives me a u value of 1. And these are very nice values for the inverse sine function. The inverse sine function likes them a lot. Provided that we remember the inverse sine is always sandwiched in between negative pi over 2 and pi over 2, so I need to only choose values in there. So it's going to be pi over 2 minus negative pi over 2. That's pi. So the perimeter of a semicircle, not including the horizontal base, of course, is pi r. So the full circle is 2 times that. And we have indeed verified that our arc length formula with a weird derivative and the square root is in keeping with what we already know. Again, this is not a proof, this is a confirmation, because pi, as you see on the right side of the screen, is often just defined as the ratio of the circumference of a circle to its diameter. But anyway, it's a cool little sanity check nonetheless. Very suave confirmation.